This is Professor Subhasish Basu Majumder, and this is a live session for my course Non-Metallic Materials. And I guess by now the 5th week is running, so you have already undertaken. This is Professor Subhasish Basu Majumder, and this is a live session for my course Non-Metallic Materials. And am I audible?
Yes, sir.
Okay. So by this time, I guess you have taken about 20 lectures, and I can understand that you might have some queries. So please go ahead and let me see that what are your queries. So we'll try to understand your question and try to reply it back. And with me, I have the TA of this course, Dr. Devashish Dash. And let me see if you can see him. So Dr. Dash is also there with you. So we are together here. So I'm waiting for your queries so that. So go ahead and ask the questions or your queries or your comments or whatever. See, the iron carbon diagram, actually, this is not part of this course because somehow I was avoiding the metal part. But yes, I can explain. Do you have any specific queries on iron carbon diagram? I mean, I do not have it handy, I guess. But what is exactly your queries? And where are you from? Agnishar. All the necessary part that I have already discussed in my lecture. For example, the eutectic reaction, the peritectic reaction. So individually, if you see, okay, individually, if you see all the relevant portion of the phase diagram that already I have described in my class. So if you have anything specific, then please go ahead. Is it only that I will have to answer through the chat box, or I can listen to the queries? Because if they ask me the question, direct question, it is also convenient. You know that at the end of the lecture, always you will find that I have mentioned the specific book, name of the book, chapter of the book, and also the page numbers. And I want you to read those original materials. So mostly I have used the book by Barsam, Fundamental of Ceramic Materials, and a book, Understanding Solids by Tilly. These are the two textbooks I have used. And also you have the common book of Callister, the 10th edition. Application of polymers, there are many applications. So anything specific you want to know? Because you know that a polymer, they have various types of application. More important thing is nowadays the composite material, where the polymer and reinforcing agents, they are used. So for example, all the sports materials like baseball bat, then the racket for the lawn tennis, and then the body of cycle, they are lightweight. Cars also they are using. So that there are many applications, and I guess that in one of the lectures I specifically uh, talked about the applications, particularly the fast lecture. You will find that I talked about it, and polymer composite lecture number 5. So that is also useful. And transformation of non-metallic materials, yes, that has been uh, discussed in lecture number 14, week 3. So anything specific you want to know about the transformation? Phase transition, in general, I have discussed in the course. But if you have anything specific about phase transition, please ask me now. Like transformation toughening is mm, that phase transition is quite important, particularly for ceramic materials. And polymorphic phase transitions we have discussed in the lectures. So, but it is very important for you to simultaneously read the book chapters, because you can listen to my lecture time and again, and you have these handouts in terms of the course materials, but it is important for you to know the text. So I understand that you have the access to these books, the reference book, and the textbook, whatever is mentioned at the end of the lecture. So that is important for you to follow. See, heterogeneous nucleation that occurs on a secondary site. So, if you consider a liquid, and liquid to solid phase transition is taking place, then always the nucleation site is not within the solution, but it is somewhere else. So, it is very important for the crystallization aspect, and surface energy that plays a major role in deciding this nucleation part. What happened? Did I talk elaborately on the nucleation exclusively?
Glass.
In case of the glass, yeah. Glass, this is important in case of glass ceramics. That is a well-known important material, where it has both the properties of amorphous glass and crystalline ceramics. So yes, their heterogeneous nucleation plays a major role. And therefore, we used to add a nucleating agent within the glass mix, so that the crystallization can take place on those material which are crystalline, but it does not melt at that high temperature, where all the glass constituents melts. But the nucleating agents, they are not melt. So whenever you cool it down, then the crystallization takes place on the uh, on this dopant, this nucleating agents, and then finally the growth takes place, followed by the nucleation. You have the grain growth, and the material turns into a crystalline phase with a very small amount of glassy phase. So in glass ceramics, it is important. Sandwich panel, potassium dihydrogen phosphate. Uh, I will No, this is, I guess, this potassium dihydrogen phosphate, you are talking about the phase transition. See, Miller indices, that is something to do with the indices of plane and direction. And unfortunately, in this course, this crystallographic part that was missing. So it was assumed that part of your other lectures you already know about it. Uh, and crystal structure is important because in many of the cases, particularly in defect, diffusion, I assume that you know about it. So this Miller indices actually that is to define the indices of the plane and the direction. So can you be more specific? I mean, what exactly you want? I mean, to explain the Miller indices. I mean, explain means exactly what you need to know. There are excellent textbook. For example, in Callister book, it is very lucidly described. So, if you have any specific question, then maybe I will be. Okay, you see that if you talk about say 110 plane, so that means the first one, the x part, and second one if it is y, and third one if it is 0, it tells that the plane should cut x-axis in unit direction, y-axis also in unit direction, and 0 means that it is perpendicular to your Z plane. So if I can draw it, then it is easier for me to show you. The board is there, but unfortunately I could not connect the board. So let me know if you can see this, what I am trying to show it here. Just hold a bit. Is it visible to you? This diagram just mentioned it here. So if you can see that this is the x-axis, this one is the y-axis, and this is the z-axis. So 110 means it will cut x-axis in 1 unit, y-axis in 1 unit, and it is actually parallel to the z-axis. So this is your 110 plane. If you want to draw 111 plane, then you will have to just cut x-axis in 1, y-axis in 1, and z-axis also in 1. So it will be just like a triangle, something like that. Can you see it? Right. So eventually what you are doing, that whatever value you can see under the parenthesis, you are just reversing it. So 1 is 1 by 1 means 1, and again 1 by 1 is equal to 1, and 1 by 0 is undefined, right? So that means it will cut the x-axis in 1 unit, y-axis in 1 unit, but it will never cut the z-axis. So it will be parallel to the z-axis. So you can easily get the 110 plane drawn. And in the next case, 111, it will cut x-axis, y-axis, and z-axis, all these three axes at 111 unit. So we'll get a triangle. Now you can go ahead and draw, say, if it is 230, this kind of plane, or minus 1, 1 bar 0, or minus 1, minus 1, 0. Then you will have to extend the this axis, not only in positive x, but you will have to extend in negative x as well. So that also you can try. So try to draw, say 230, how it will look like. So it will be half, 1/3, and again it will be parallel to z-axis. So in fact, you can draw any Miller indices thus in this way. Is it understandable? Could I explain it? Because explicitly somehow I could not describe the crystal structure. Yeah, this is Surinder. Good to see you. And this is an important question, this curvature part, right? So in most of the case, this is true, whatever you have asked. But to tell you the truth, that in case of polymer, as I understand, it depends on the chain structure, of the polymer. But exactly why this the curvature is either positive or negative, this part is not very clear to me. I'm sorry to say, because as you understand that I am not very I am not an expert in polymeric material. So curvature is related to its chain structure. that is sure. But why it is positive or why it is negative curvature, this I cannot answer. So this part for particularly elastomer and polymeric material, we have seen it, but why the curvature is convex or concave type, it is not clear to me as well. But it happens. It is related to its chain structure, branching, unlike the normal metal uh, or ceramic material. Ceramic is very straightforward, as you understand. This is it undergoes a brittle fracture, so stress strain curve is always straight, and the curvature, whatever you see in case of metal, that is due to the dislocation movement. So when it plastically deforms beyond the yield point, then you know that this one is changing its curvature. But this is an interesting question. Let me think on it and be in touch with me, and I will reply you back. Let me read it. That why it is convex or why in some cases it is concave in nature. But this is a good question. In fact, all the questions are good, but this is interesting. I mean, I will have to think on it. So, Agnishwar, you go and read the chapter by Callister, the initial few chapters, and that will explain that will in fact clarify your understanding on the Miller indices, plane, direction. And another book is the book by Askeland and Fule. I guess I will write their name properly. This is also a book on material science. The title exactly I don't remember. That also describes this Miller index quite nicely. Please go ahead and read these two books. And if you have any further queries, and be in touch with me, send me an email. I will try to explain it. Or maybe we can have separate Zoom session and to explain these things better. So I also understand in this course little bit crystal structure description I will need to add, because that is required. I assume that you all know this as a part of your other course. This is Askelan and Fuller, right? We second book. But a board work may be necessary. I mean, is it possible for me to toggle between these two? Um, you know, the brittle fracture, that is basically elastic in nature, right? So you have a stress strain diagram which is straight, and the slope is the elastic moduli. So if you have a very steep slope, then that means elastic modulus is quite high for that ceramic material. And then suddenly it breaks, right? So it breaks suddenly, unlike metal. So take an example, take a glass plate, and then you apply, say, tensile load. So you will see that there is a very small strain, and stress strain curve is quite linear in nature. And then suddenly it breaks. That means what is happening, that there is a small initiation of crack and its rapid propagation. There is no mechanism to stop it. right? So whenever there is a small crack initiated in the material, this crack propagates and you get two surface out of it. So energetically, if you see that when in a glass plate, you are applying a tensile load, then this energy that you are spending, that is stored as elastic energy within the glass. Okay. Now, one point will reach where this energy, the glass will not be able to withstand this energy. So there will be initiation of a small crack, and this crack will just propagate, and there is no mechanism to stop it. So that is brittle fracture. In case of metal, what is happening that this energy is stored in initial case. Then, whenever the crack generates, there are a lot of dislocation is there. So dislocation starts to move along with the slip plane. So there is not a catastrophic failure. So the strain energy is spent to move this dislocation along with the slip plane, along the slip planes available. So you need two things. First, sufficient concentration of dislocation, which is there in case of metallic material, and also the slip plane for their movement. So when you have these two things, then you will see that it will have a elastic region followed by a plastic region, and the material will not fail catastrophically. But in case of brittle fracture, you either have very low concentration of dislocation, or even if you have dislocation concentration is there, but you do not have sufficient number of slip planes available for their movement, so they fail catastrophically. So that is due to this fact the ceramic fracture um, undergo a brittle fracture, catastrophic failure, straight stress and strain behavior. And I guess in some of the lecture, let me tell you, if you have uh, module 4, lecture number 18, lecture number 19, this brittle and ductile material and fracture mechanics, that has been clearly mentioned. Okay. So, mm, Tejas, you are talking about sleep condition. This sleep is having a different spelling, right? So this is slip, slip plane, and slip direction. These two will decide the slip system. Again, understand the slip system, you need to know about the crystal structure. And I am feeling that I should have taken the crystallography, at least the preliminary things, because you know that it depends on the uh, high density um, planes. You know that in a crystal structure, if you talk about the FCC structure or BCC structure, so along with these planes, you can see here, so if it is a FCC structure, in the corner, each corner you have one atom, and also in the face centered position, some atoms are there, right? So now, um, uh, if you just consider various planes like 110 plane, 100 plane, 111 plane, then you can basically tell that at what uh, in which of this plane you have the higher density of these atoms. So basically those planes will act as a slip plane. So the slip plane and slip direction will eventually decide your dislocation movement. So that is important in case of metallic system. But in non-metallic system like ceramic, you have do not have enough concentration of dislocation, or this kind of slip system available, enough slip system available. So therefore, the fracture is always is of brittle type. Super cooled liquid other than glass. So any system which will give you the formation of the glass, that will behave like this. So once you cool it down, then at the melting point there is not sudden change in the specific volume. um, Uh, just a moment. I mean, just let me explain Mohak Jain's question. So, I guess you are following what I am trying to say. That there are glass former like silicon dioxide, B2O3, P2O5. So they are known glass former. So in case of known glass former, when you cool it down, then it solidifies, but there is not a jump in specific volume. The specific volume does not change abruptly at the melting or freezing point during cooling. Now, it is possible for you to have a supercooled liquid in case of certain mixture who are not individually glass formed, but two oxides, when you mix them together, they can behave like a material, another material, which undergoes this liquid to glass transition. So in that case also, you have a supercooled liquid, right? So it is not only that the glass former, it does the thing. One good example is calcium silicate. Although the silicate, no, I should not take this example, because SiO2 is a glass format. But some these two oxides, when they mix together, they form like a uh, glassy nature. I mean, they are not a individual glass format, but as a mixture, they act like a glassy material. So that is there. Um, Uh, Actually, Krishna Prasad, what is your question? I did not get it. One is stress relaxation in polymers concave curve. Can you explain it a bit more? And also in safety glass, crystallites are created by annealing and its brittle fracture properties are altered. Safety glass means you are talking about the tempered glass. So in tempered glass, it is the heat treatment that creates its safety property. So the surface is cooled, so it is already in under compression, and you will have to overcome this compressive stress before it fractures. So that is there. So that is the safety glass. If you are talking about bulletproof glass, then the laminations are involved. So in between the glass layer, there is a polymeric layer involved in it. And if you are talking about the crystalline glass, which we call glass ceramics, then it is true that you have some kind of nucleating agent, and crystallization takes place during the cooling from the molten state. So these three are three distinct one, and I guess in um which lecture? Lecture number 17, I have described this. Lecture number 17 is specialty glass and glass ceramics and specialty glass. So, oh, you are talking about the tempered glass. Yeah, tempered glass, it is true, but that is either by uh, some physical mechanism. For example, ultimately, you will have to induce compressive stress at the surface of the glass. So that you can do either by uh, making a cool air shot at the glass surface. So still it is in the molten, semi-molten condition. So the surface will have a compressive stress and the inner part will still under tension, and then it will freeze. So that mechanism is one. Or you will have to dip the whole glass plate in a chemical bath where there will be ion exchange. So sodium ion will be exchanged with a larger potassium ion. So that will introduce a compressive stress at the surface. And this is chemical strengthening. Both this effect I have described in my lecture number 17 in module 3. Factor of safety in manufacturing area, you know that you will see the description. I will describe it, but I guess in module number 11 I have described it in design of ceramics, right? Wearable distribution. You see, in case of brittle material, Tejash, I am answering your question. In case of brittle material, if you take a number of samples, say 10, 20 samples, and you fracture them, you will see the fracture stress. They are different for each sample. So the first one maybe 110 megapascal, second one is 115, third one is 80, fourth one is some other numbers. There is a wide distribution. So if you want to use that material for any structural application, then what you should do? Because you do not know that for which particular stress, till which particular stress it is safe to use. So a normal thing is do the averaging, but this is not the right way to do. So in that case, we actually estimate the design stress. So design stress is related to a probability. I can tell the customer that if you use this ceramic or any brittle material, then 99% with 99% probability, this will not fail at a stress level, say 80 megapascal. So that is known as design stress. So here the factor of safety is important. So this factor of safety is that you define the design stress of your material, say 100 megapascal, and you confirm that 99% of the material will not fail below 100 megapascal. So there is a procedure involved in doing that. So this is known as Weibull distribution, Weibull statistics, a statistical method. How to determine it? I will describe it in lecture number 58 towards the end of the course. It is design of ceramics. So I have not yet, I mean, you have not yet gone through this lecture. So there we will get the answer in details. Krishna Prasad, where are you from? I mean, and what is your question? Um, what's this? What are the stresses taken into account? Oh, yes. So stress relaxation in polymer. Yes, that is true. So this much I also told that this is related to that. But the question is that why only concave or why only convex, this the curvature of this curve. That was the question. So I think we need to dig a bit further to understand that problem. So that is why I told Surinder that I will get back to you. Um, I know him because you know that he did his MTech from our institute, IIT Kharagpur. So, okay, so absence of gravity dislocation will reduce in ceramic. You know that dislocation density in ceramic is usually, in most of the instances, they are low. So I've never thought in that way, Mohak, that in absence of gravity, what will happen to the? I will have to get back to you. This I have not thought about it. But in general, the dislocation density is relatively lower as compared to metal. That is number one. And also the slip system, the combination of slip plane and slip direction, that density is also low in case of ceramic. So they undergo brittle fracture. All the oxides, glass material, you will see that brittle fracture. It undergoes brittle fracture. Glass tempering, briefly, I have just a few minutes back I was talking about it. You know that the idea of tempering is to induce compressive stress at the surface of the glass. So you know all the ceramic material, they are weak in tension but strong in compression. So you will have to overcome this compressive stress uh, before the tensile load take over. So the surface need to be under compression. So how you can do that? So you can do that by increasing the glass temperature beyond this glass transition temperature. So it is a plastic rubbery kind of state. And then at the surface you put the cold air shot. So cold air through a nozzle you just put at the surface of this glass. So it will be compressed more, and the inner part will be still under tension because glass is a thermally non-conducting material. So inner will be under tension, the outer surface try to be under compression, and then you just cool it down to room temperature, and you will have a compressive stress region at the surface. So this is physical tempering method. And then you can also do another thing. In the hot state, you can dip the glass inside a molten a solution bath of potassium ions. So you know the glass, soda lime silica glass is having sodium ions. So these sodium ions will get replaced by the potassium ion, which is larger in size. So when potassium ion is replace the sodium ion, it will induce a compressive stress at the surface. So effect is same for both the cases. So one is physical method, another one is chemical method. So once you temper the glass, then it is more stronger as compared to normal glass. So if you try to break it, then you have experience. When you see sometimes accident takes place, then you will see the car headlight, etc. It falls, the glasses falls right there before acting as a splinter. So if the glass is not tempered, then this glass will be just like a splinter in case of accident. So in case of tempered glass, it will just be broken and fall in the same place because of this effect. Gas carburizing. Did I talk about it? Carburizing. This is where from you got this term. It is the carburizing of steel, the metallic material. So that is related to that. It was not part of my lectures, I guess. So is it a general question or uh, in which lecture it was described? Gas carburizing. But in general, you know that since you are asking about it, this is related to carbon diffusion in metal like steel. Usually methane and carbon monoxide is used. There's a mixture of these two gas, and in gaseous form, it catalytically dissociates into the carbon, and temperature is high enough for this carbon to diffuse inside the steel. So that is the basic fundamentals of gas carburization, but it is related to metal. I have not talked about it in any of my lectures, but since you have asked, that is briefly I can tell. So a mixture of methane and carbon monoxide catalytically dissociates into carbon, and then this carbon diffuses inside the steel material. So that is gas carburization. Oh, I see. So that was a question. Yes. So that is the answer. Then you can tell a gaseous atmosphere, mostly carbon monoxide and methane mixture. So these two gases catalytically they diffuses on hot steel surface. Um, Catalytically dissociates in fact to form carbon, and this carbon diffuses inside the steel lattice to form a carbon enriched surface layer. So that is the fundamentals of gas carburization. Uh, Glass, Mohawk, glass is 100% recyclable. So that is why it is good to have glass bottle for Pepsi and other cold drinks. Yes, that is recyclable. But tiles and pottery ware, you know that once the clay is uh, heated and it forms a mass which is almost a dead mass. So you can use it. This is called in ceramic language grog. So part of it can be used while making the fire clay bricks or other refractory material. Uh, but most of it, I should say, that they are not recyclable. Maybe 10-20% you can recycle it, but glass is 100% recyclable. Uh, Krishna Prasad, do carbon fiber nanotubes fit into this? Fit into what? This is a carbonaceous material I described. I think this was my lecture number 11 in week 2. But fit into this means what? Can you elaborate? What do you mean by fiber nanotubes fit into this? So what is this? Tejash, I understand you are solving the assignment. Um Now, you see that the assignment problem, if you look at it carefully, it has mostly two types of question. One is objective type, and the answer you will be able to answer all of them if you study the lecture files, the handouts thoroughly, most of it. And there are another types of question which is related to your understanding, and they are numerical problems. So these are the two types of problems that usually I ask in case of assignment. And if you are following my lectures along with the study materials means the book chapter, whatever I have given at the end of my lecture, you can solve most of the assignments. Now, if you can solve most of the assignment, then I am pretty sure you will be doing well in the exam as well, because the exam will test your basic understanding on this related materials. So if you are serious about this course, you are doing the assignments, you are reading the chapters well, you are following my lectures, then I'm pretty sure that you will do well in the exam as well. Yes, Krishna Prasad, question is, can we theoretically, maybe some part of your question I am missing. So that's why and as you said correctly, that it is interrupted by the question of others. So I could not get the question. So you can just directly ask me question. Let me give you the, should I give your, so you can ask the question. Questions. কত is at
CGCRH, CGCRH, @gmail.com. Session close করতে বলছে।
So let us start today, and thank you so much for all your queries, and stay tuned with me, and I have given the email ID. You can consolidate your question and ask me there, and as far as practicable, certainly we will um, get back to you, and be in touch and study well. Thank you so much.